In this video, I will talk about the molecular geometry and VSEPR theory. At the end of this video, you will understand what is the VSEPR theory and the logic behind the molecular geometry. So first, what is the VSEPR theory? Valence shell electron pair repulsion. So valence shell, as you remember, these are the valence electrons. And electron pairs are bonding pairs and the lone pairs. And there are interaction between the bonding pairs and lone pairs. And this model tries to understand the shape of the molecule by using the repulsion. So firstly, we have to consider the valence electrons. And as you remember from my previous videos, we need to know the Lewis dot structure. Why? Since by using the Lewis dot structure, we can see the lone pairs and bonding pairs together. And I can give an example. What is the bonding pair and the lone pair? We can consider a molecule, for instance CO2. And CO2 has this kind of Lewis structure. Oxygen atoms have lone pairs. These are the lone pairs. And these are the bonding pairs. And there is an interaction, so repulsion, actually between the bonding pairs and the lone pairs. And this molecule is 180 degree. So this bond is 180 degree. The reason is that repulsion between the electrons is minimal in this formation. For instance, if the CO2 has a band structure, something like this, so the repulsion between the electron pairs and bonding pairs increases. So this is not a stable conformation, molecular geometry. This is not a stable molecular geometry for the CO2. So, as a summary, we need Lewis dot structure, and you have to know this to predict the molecular geometry. And secondly, we need to know the class of molecule. What is the class of molecule? Class of molecule is, for instance, A, B to E. So here, A is the central atom, B is the atom around the A, other atoms, and E is the lone pair. And I want to give an example, for instance, SO2 molecule. So firstly, I need to draw the Lewis dot structure of the molecule, and I want to give the Lewis dot structure very quickly. So we look the central atom, okay, and this is the E, lone pairs in the central atom. So we have an E, and we have 2B, since there are 2 oxygen atoms, and we have 1 central atom. And this is the class of the molecule, and we can use it to predict the structure of the molecule or the molecular geometry of the molecule. But even if we don't know the class of this molecule, we can predict it, right? The reason is that there will be a repulsion between the bonding pairs and the lone pairs. And I also want to give another important property. Lone pair repulsion is bigger than the lone pair bonding pair, and bonding pair repulsion is the smallest among them. So by using these three information, I can predict the geometry of the molecule. Since to minimize the repulsion, I have to put the oxygen atoms in a banded structure. In this way, this lone pair will interact with bonding pair, but also repulsion between the oxygen atom will decrease. So this should be a stable configuration for the molecule. However, I can also predict the bonds. What is the bond angle? So according to the VSEPR theory, the bond angle approximately 120 degrees. However, lone pair bonding pair interaction is bigger than the bonding pair, then this angle should be bigger than the 120 degree, and this is also should be bigger than the 120 degree, and this angle should be smaller than the 120 degree, since bonding pair interaction is smaller for the lone pair and bonding pair interaction. But these are the details, and maybe I can make another video for this concept. And this is the table that students have to know before the general chemistry exam. If the VSEPR theory is included in the exam, you have to know this. And we can look at the some molecules. We look at the SO2, and we can look at the ammonia molecule. Firstly, we need to draw the Lewis-Dot structure. So nitrogen has lone pairs, and there are three bonding pairs for the hydrogen atoms. As I say, lone pair bonding pair interaction is bigger than the bonding pair interaction. Therefore, this angle between the bonding pair and the hydrogen and nitrogen bond is more than 90 degrees. And this molecule has a trigonal planar shape. So nitrogen is on the top, and it has a structure something like this. Hydrogen atoms is in the bottom, and it creates a triangle. Therefore, it's called as trigonal pyramidal. The other example is water. We can draw the Lewis-Dot structure of water first. So water has two lone pairs, and it's connected to the hydrogen atoms. The angle between the two hydrogen atoms, so this angle is 104.5 degrees. Again, the reason is that lone pair interaction among the bonds and interaction between the lone pair. And this molecule has a band structure. The other structures also in here, but even if the structure is not here, and I will make a harder example, we can predict the molecular geometry. But again, it needs a little bit experience. To be safe, the best way is to look to the table, something like this. And what is the molecular geometry of PCl5? So phosphorus has 15 electrons, right? 2, 8, 5, and Chlorine has 17 electrons. Chlorine has 17 electrons, and this is the electron configuration of the chlorine. So I am drawing the Lewis-Dot structure. So phosphorus has 5 electrons, and chlorine has 7 electrons. So this is the Lewis-Dot structure. To make it easier, I can combine the dots to represent the bonding pairs. So there is no lone pair in the p atom, as you see. So the class of the molecule is AB5. If I look at the table, there is no AB5. We have AB5E, the closest one. So if I look the molecule AB5 here, instead of this lone pair, I have another atom, right? And I can predict the geometry, since if I look to another one, AB2E3, there are 3 lone pairs, and this is a stable configuration. Trigonal by pyramidal. So in our case, phosphor p atom will be in the center, and it will be connected to the chlorine atoms, 3 chlorine atoms in equatorial position. So there is a plane here. Okay, and I will put the other 2 chlorine atoms in axial position. By the way, these are called as axial, and these chlorine atoms are called as equatorial position. And the expected shape is actually trigonal by pyramidal. So this is the shape of the PCl5.